How's everyone who's watching this? This is my 33rd video on the channel, and today we're going to be finishing Chapter 2 of Intensive Science and Virtual Philosophy by Manuel DeLanda, titled The Actualisation of a Virtual in Space. Last time, we looked at how intensive processes give rise to extensive quantities and qualities, using embryogenesis and species as case studies. In this video, we'll delve deeper into what exactly intensive properties, or rather intensities, are, bringing the concept out of the realm of thermodynamics and properly into philosophy. Without further ado, let's get started. DeLanda begins by quoting Deleuze himself, who says,
"We know intensity only as already developed within extensity, and as covered over by qualities."
The purpose of the rest of the chapter is essentially to figure out what we have to do to overcome the disguising of intensities. However, before we get to that, we need to know what exactly Deleuze means when he uses the term. To this end, DeLanda says that in thermodynamics, a property is said to be extensive if a quantity of mass containing it being split in two halves it, whilst it is intensive if the split parts have the same amount of a property as the original, represented in this diagram. To give some examples, volume and mass itself are both extensive, whilst temperature and pressure are intensive. Even if you pour out half a kettle of water, it's still going to be boiling away. This definition is useful, but isn't quite what Deleuze means. This is because its focus on dividing allows us to apply it to qualities, like colors. As we saw in the quote, this is problematic, since he opposes the intensive to both the extensive and the qualitative, not just to the former. Here, another way of defining properties appears promising, the one used by physicists. For them, extensive properties are those that can be added up simply, whilst intensive properties are those that can only be averaged. For example, if you put two areas together, you get a proportionally larger thing. The property is extensive. However, if you add two temperatures together by placing objects containing them next to each other, they're going to average out to some sort of thermal equilibrium. The reason this is interesting to us is that it points to a certain dynamic aspect of intensity. By this process of averaging, in DeLanda's words,
differences in thermodynamic intensities are capable of driving a process of equilibration in a population of molecules.
In this way, differences in intensity organize fluxes of matter and energy, something qualities like color cannot do. However, this definition isn't perfect either. There's still a couple more distinctions we still have to make, starting with the fact that intensities can in fact be divided. However, these divisions, unlike those of extensities, lead to changes in kind in the system they occur in. A rectangle cut in half is still a rectangle, sure, but a system that has its temperature divided in two is now in a very different condition. Going farther, a big enough change can lead to a critical threshold being reached, leading to radical changes in a given system's extensive properties as it enters into a new state. Given all our talk about species and populations last time, this might all sound quite abstract in comparison. However, this modified definition of intensity works quite well when considering these phenomena. Rates of change involving things like births, deaths, and general growth act surprisingly similar to thermodynamically intensive properties like temperature. Although they might not drive processes on a molecular level, they still do so on larger scales, like can be seen in the case of migration, a process spreading out across the species as an individual. This isn't to say that the thermodynamic is the same as the biological, something that obviously isn't the case. Both systems are structured by singularities or attractors, it's true, but unlike on the level of thermodynamics, there's something else at play in biological systems, that being what Deleuze terms affects. This term, borrowed from Spinoza, concerns the capacity for an entity to interact with others. In other words, the capacity for something to affect and be affected. Just like singularities, these affects are virtual. They are never completely actualized. However, unlike singularities, they can't really be explained with the intensive as we've looked at it so far. Before we get to why though, some background on how affects work will be well worth it. Essentially, at least in DeLanda's eyes, their main function is to allow for the creation of assemblages, one of the most infamous of Deleuze's concepts. These assemblages are made up of both organic and inorganic individuals, like in the case of an animal walking on solid land and interacting with a gravitational field. It's possible to study each of an assembly's components individually, but it's only through looking at how they interact with each other that we can appreciate their affects. In order to take this into account, we need to expand our definition of intensive even further. Concerning the production of assemblages, DeLanda says,
An assembly process is said to be characterized by intensive properties when it articulates heterogeneous elements as such.
For example, in the case of the animal land field assemblage, each component is heterogeneous, even when combined together. The animal is never the same as the ground it walks on, or the gravitational field that keeps it from floating away. We can thus say that intensive processes first and foremost relate difference to difference, like rates of change to rates of change. In this way, we can look at an ecosystem as an intensive assemblage composed of a diverse range of components, distinct themes, changing weather conditions, variety of geographical features, and so on and so on. They are never truly homogeneous. With this broad definition, we can now tackle how the virtual and intensive seem to be concealed by the extensive and qualitative. Central to this, DeLanda says, is the cancellation of difference, something that impacts both singularities and affects. In a dynamic system, these two virtual components are clear, trajectories arcing around singularities, and heterogeneous elements entering in and out of assemblages together. However, when the system is made uniform, all this disappears. Suddenly, differences and their interactions with each other seemingly go up in smoke, intensities being covered over by extensity and qualities. Although this process is often blamed on scientists, it also happens naturally, like in the example of how intensive differences cancel themselves out when reaching equilibrium. There are therefore areas of what DeLanda terms objective illusion, places where the processes that give rise to objects are hidden by the product itself. This adds a new thermodynamic-inspired layer to how we've been able to approach systems and their singularities. However, to begin with, it would be worthwhile to distinguish between two different types of system. Firstly, there are what DeLanda calls linear systems, one where there's only one attractor or singularity that trajectories continually move towards. Secondly, there are nonlinear systems, systems where there are a number of so-called answers or attractors. It's the second case that concerns us now. Basically, in order to avoid illusion, we have to keep in mind whether or not a system is close to or far away from equilibrium. This is because, by definition, a system near to equilibrium, even if it's nonlinear, can only exhibit one tendency at a time. To understand the complexity of a nonlinear system, DeLanda says,
Appropriately large differences in intensity need to be maintained by external constraints and not allowed to get cancelled or be made too small.
Basically, the system has to be driven out of equilibrium, described in Deleuze's language as a low zone of intensity. Nonlinear systems are generally better at showcasing the virtual when compared to their linear counterparts, since there are always multiple singularities that exist outside of the one of a process of actualization at any given moment. However, in a low zone of intensity, they become effectively linearized, to borrow directly from DeLanda. This is how many scientists amplify an originally objective illusion, and why Deleuze prizes far from equilibrium thermodynamics as a field. Philosophy, in the French theorist's eyes, must move away from a study of qualities and extensities towards that of intensive processes which produce them, so that it may be able to open a window into the virtual. To demonstrate what this might look like in practice, using biology rather than philosophy, DeLanda offers the example of the tetrapod limb. This structure can take a myriad of forms, from bird wings to human thumbs, thus making it difficult to group its actualizations together based on any qualities or extensive properties. However, if we begin right at the start, right at the point where it begins to take shape in embryogenesis, we can see that the same processes give rise to these divergent results. Obviously, the particularities of a process vary, with some bifurcations occurring for certain species and not others, but the same intensities are at play. We get a glimpse of a virtual limb. However, that's all it is, a glimpse. We need to go deeper if we want to explain the source of what the processes have in common. At this point, before outlining the second step, DeLanda takes a step back to return to a metaphor that we've already looked at a couple of times by now. The general gist of it is that topological space gets progressively more and more specified as it moves down a hierarchy of geometries, until it eventually takes a Euclidean form familiar to us. DeLanda wants to update this metaphor. Instead of talking about Euclidean geometry or topology, we should concern ourselves with extensive structures and the virtual, respectively. Likewise, the intermediary steps, originally represented by projective and affine geometry, should be replaced by intensive processes. Finally, each space connects to each other by their affects. In this case, this means the transformations available to them. the ways they can be changed while staying the same. The purpose of this metaphor is, in DeLanda's words, to underline that
we need to conceive a continuum which yields, through progressive differentiation, all the discontinuous individuals that populate the actual world.
However, this continuum isn't some sort of homogeneous space like might have been implied through the use of topology to demonstrate its properties. Rather, it's completely heterogeneous, full of multiplicities that are topological spaces in their own right. DeLanda calls the virtual a space of spaces, or, to use Deleuze's term, the plane of consistency. At this point, there are two things we have to address before we can move on. Firstly, the description of multiplicities as concrete universals that we talked about in the first two episodes of a series was too reliant on mathematical, actual models for philosophical virtual entities. Secondly, we spent so much time on singularities that we've left affects, plus our fleeting description of them earlier, neglected. Our first task, DeLanda says, is to take Deleuze's mathematically inspired concepts, namely singularities and differential relations, and get rid of their actual elements. To do this, we have to make sure that none of them presuppose individuation, a wonderfully nebulous term that can be explained using the example of functions. Basically, as seen in this diagram, functions take an input and spit out an output. When a mathematician or physicist talks about differential relations, this is always what's lurking in the back of their mind. They are first and foremost processes of individuation, in the sense that they take something and give it a specific identity. DeLanda illustrates this fact with the example of mapping the differential relations of a physical system. The input, independent variables, becomes the dimensions of a state space, and the output, dependent variables, individuate the specific status of that space at a given moment, a collection of such outputs creating a trajectory as time goes on. So, how do we escape this individualizing view of viewing the virtual? Essentially, we have to think of differential relations as so-called formless functions, where neither inputs nor outputs are distinguishable. As DeLanda says,
the relation is not a rate of change of one quantity relative to another, but the rate at which two quantities change relative to each other.
Deleuze himself terms this reciprocal determination, where difference relates to difference without anything standing in the way. Having now looked at virtual differential relations, let's take a peek at virtual singularities. These can only properly be grasped in the vector fields we talked about last episode. To put it simply, a vector field is a collection of instantaneous values for a rate of change that haven't yet been turned into trajectories. In other words, a field occupied by a myriad of pre-individual entities. As seen in this diagram, as the spots devoid of arrows, these entities allow us to perceive topological invariants, places without any movement. These invariants are one and the same with singularities, their occurrences being described as ideal events by Deleuze himself, ideal in the sense that they are never actually fully actual. Every singularity is defined by its ability to be prolonged into an infinite series of these events. To give a metaphorical example of what this means, take the phase transition from steam to water that occurs at around 100 degrees centigrade. Between this singular event and the next major phase shift, from water into ice, there are an infinite number of points, every infinitesimally small change in temperature. Taking this out of metaphorical, singularities work in much the same way. Between each singularity is a similarly infinite series of events, extending up against different multiplicities. Considering how this can be used to construct the plane of consistency, weaving multiplicities together, each series of events emanating out of a singularity can be taken as a continuum that connects them all together. This must be nuanced, however, by the fact that multiplicities do not interact with each other. In Deleuze's words, multiplicities are impassive. Here, affects come into play. Whilst in the actual, these refer to capacities for both affecting and being affected, these two aspects are split up in the virtual. Multiplicities have a pure capacity to be affected, but they can't impact other things. Rather, there's something else also at play, what Deleuze terms the quasi-cause, which has the pure capacity to affect. The purpose of introducing this entity is to explain how multiplicities are transformed virtually. Rather than creating anything, Deleuze is insistent on the fact that this quasi-cause only operates. It simply connects series of events together. Nothing more, nothing less. To explain how the quasi-cause functions, it's at this point that DeLanda introduces the field of abstract communication theory. Here, series of events are related to each other in the form of what are termed information channels, relations that modify the probability of the events that the series are made up of. As DeLanda states,
This definition of an information channel appeals to Deleuze precisely because of its highly abstract nature, presupposing nothing about details of physical implementation.
however, the concept isn't truly pre-individual if we assign numerical values to each probability. In the virtual, we can't say that something is 50% more likely to occur than something else, for example. Instead, events can only be considered in terms of being rare or common, singular or ordinary. They are related ordinally, in other words, in terms of first, second, or third most likely. Through the creation of these ordinal information channels, the quasi-cause is able to keep multiplicities in flux, shaking up distributions of singularities, something DeLanda says he will further develop in the coming chapters. Now, this concludes the second half of Chapter 2 from Manuel DeLanda's book Intensive Science and Virtual Philosophy. I truly hope you enjoyed or learned something, and if you feel I got anything wrong or wasn't as clear as I could have been, please do feel free to let me know in the comments so I can do better. Next time, we'll start Chapter 3, titled The Actualisation of a Virtual in Time, and begin our exploration into the temporal side of Deleuze's ontology. Until then, bye!